So to illustrate the Canny edge detector, I'm going to use this picture of Lena. Now, this was a picture that was used for image processing a lot. Some guy, he cut out just the top part of a picture from 1972 of Lena Soderbergh, I think was her name, because it appeared in a men's magazine. So he used just the picture. And by the way, this is Lena recently, so we all change. But here's our Lena image, and if we were to take just the magnitude of the gradient, we get a value that looks like this. So you see it's close to edges, but actually you and I see edges, right? It's just a gradient image, right? So then we can threshold that gradient. So now you can see a bunch of that stuff has gone away. So anything where the gradient is not high enough has been removed. And then we do an operation called thinning, and we'll talk more about this in a minute. The fancy name is non-maximal suppression, basically saying if I've got a bunch of points that exceed a threshold locally, let me only pull out the point that exceeds it the most. We'll talk about that in a second. When you do that, you get something that looks like that. All right, so that you go back and you can see there's the thinned version of that. Just a quick note about why you have to do the thinning. All right, so let's take a look at this little area here. You can see that there is this kind of thick part that exceeds the threshold. And what we would like to say is that there's an edge running through the middle. So if you think about it, if you're coming across here, you might see a profile that starts low and then goes up high. All right? And if you take the derivative of that, you'll see that the derivative over this area is above this threshold. So that gives you this thick edge. And we want to turn it into a thin edge. So the way the non-maximal suppression, the thinning, is done in the Canny operator is as follows. And you're not going to have to implement this. I just want you to be aware of what's going on. Basically, it finds areas of high gradient, and it looks across in the direction of the gradient, and it finds just the peak there. And then over here, same thing, it would find the peak here. Here the gradient is in that direction, so it would find the peak there, right? Sometimes, and that's what this picture is showing here, sometimes you have to interpolate, right? You find the gradient, you say, okay, I think it's somewhere in between 2 pixels, so you can actually get sub-pixel accuracy. But the point is that it basically looks perpendicular to the gradient in order to find the maximum. So that's how you do the thinning part. And now there's one very clever detail to look at, all right? If you take a look at this point sort of under the chin here, you'll see that some of the pixels did not survive the thresholding, okay? And it's a problem because you could say we had too high a threshold, but the problem is if we make the threshold too low, then a whole bunch of stuff is going to show up that we don't actually care about. So the question is how to deal with that. So this is what John did and the hysteresis. The first thing we do is we apply a high threshold to detect strong edge pixels. So the threshold pulls out a bunch of pixels. Then what we do is we can link those strong edge pixels to form strong edges. Okay, so far not so clever. Here's where the clever part becomes. We now apply a low threshold to find weak but possible edge pixels, and then we extend the strong edges following the weak pixels. So what that means is that if an edge only has weak pixels on it, it doesn't get found to be an edge. An edge can only be found if some of the pixels are strong edge pixels. The assumption here is that all edges that I care about will have some strong pixels in them, and then I might have to continue through a weak area, but the edge got initiated by the strong detections.